At this point, we've just been dealing with force vectors generally, okay? But there's another type of vector that we very commonly use in statics, and that's a position vector. And really, a position vector is just a vector that locates a point in space. So if I've got point P, as I do up here on the picture, okay, I can draw a straight line from some fixed origin up to that P. And the vector going from that origin up to P is my position vector. Okay? And I would write that just like I would write a force vector, any other vector in 3 dimensions, okay, with I, J, K components. Okay? So I would have an X distance, and this would just be like meters or feet, inches, millimeters, something like that. So I move some amount in the X direction, some amount in the Y direction, some amount in the Z direction to go from the origin to the point P. Okay, so that distance X, Y, and Z is written in Cartesian form, just like written right over here. Okay, so that's the absolute position, but a lot of times we want to know a relative position. That would be a position between 2 points, such as the position from A to B. And you'll see me typically write that as R sub AB. Okay, so in doing that, again, all I'm doing is I'm trying to figure out how much in the X, Y, and Z direction I move to go from A to B. Okay, well, I can write A and B in their vector form relative to the origin, just like we did up here. So I have the position vector A, the position vector B. Now, using vector addition, you can see that RA plus RAB, the vector between A and B, equals RB. And that's what I have written on this top equation right here. And that's just vector addition, right? This vector plus that vector equals this vector. So rearranging that and solving for the position vector between the 2 points, RAB, is just going to be the position of B minus the position A. It's always final minus initial, basically, where you're going minus where you started. Okay, so that can basically, I can do that for each component. Basically, final minus initial in the X direction, final minus initial in the Y, and final minus initial in the Z. Okay, and that's really how I can find a position vector between 2 points. Just take the final position minus the initial position. Okay. Now in class we'll do it a little bit differently when we solve problems. I think it's better just kind of think, okay, well, how much do I have to move in the X direction to go from A to B, in the Y direction from A to B, and so on. But mathematically it's just final minus initial. Okay. Now, why do we ultimately want to use this? Well, because oftentimes we write a force directed along a line. That would be like a cable or a rope, as I have here, right? I'm pulling on it with a force. I know that the force is directed through that cable. So if I can find the position of that cable, I should be able to write the force in Cartesian form. Basically, give the magnitude of that force a direction by knowing the position vector of this cable right here. So in order to do that, I need to talk about a unit vector. Okay, and a generalized unit vector, not the specific ones, the I, J, K, corresponding to the X, Y, Z. Okay, in general, a unit vector is nothing more than a dimensionless vector having a magnitude of 1 in some direction. So I have this U vector. I can give it a value of 1 and just say, hey, it's pointed in the direction of this cable, in the direction of this force, okay, in the direction of this position vector. Okay. So all I need to do is figure out how to get that to have a magnitude of 1 in that direction. And I do that simply by dividing any vector by that vector's magnitude. So any A vector divided by the A vector's magnitude will give me my unit vector. So similarly, I could take, if I know my force vector, I can take the force vector divided by the square root of the sum of the squares. That'll give me the unit vector. That would be a vector with magnitude 1 in the direction of my force vector. Likewise, and what we typically do is we use the position vector. So if I know the position from A to B, if I can find that R vector going from A to B, okay, I can find the magnitude of it by taking the square root of the sum of the squares and just divide that R vector by its magnitude and get that unit vector. Okay? Then from that, I can actually write my force in Cartesian form. So if I know, say, I've got 10 pounds, I've got some magnitude of force up here, I can take that magnitude of the force times the unit vector. That will give me my force vector. And it's essentially just rearranging this equation, just bringing F over to this side. Okay? Now, I substitute in what I know about my unit vector was just the position vector divided by its magnitude, which is generally easier to find, right? I can measure the length of this cable, its position. Okay, I can find its position vector. I take its position vector divided by its length or its magnitude. Okay, that will give me the unit vector. And I can write that force along that line as the magnitude of the force times the position vector from A to B divided by the magnitude or the length of that cable from A to B, which gives me the unit vector, gives me the direction, which again I'm multiplying by my magnitude of my force.